Good morning, class. In this video, I will talk about how to carry out a titration. First of all, let me explain some common terms to you. The first one is quantitative analysis, which is used to determine the quantity of the materials. For example, the number of mole, the mass of a chemicals in the substance. For example, wastewater is produced from a electroplating plant, and the wastewater contains the precious silver iron. Some other recycling plants want to buy the wastewater and want to regenerate the silver metal from the wastewater. So chemists need to know the concentration of silver iron in this wastewater in order to fix the price. So chemists will carry out the analysis. The analysis may involve the accurate measurement of volume of a standard solution used. Then, as the volume is involved, these kinds of analysis are usually called volumetric analysis. Titration is the name of the technique to obtain the volume of the solution during the analysis, and usually the solution is added from a burette. There are 4 major types of titration. You will have the chance to perform the first 2 titration in your SBA. This compensometric titration is not in our DSE syllabus. And the last one, precipitation titration, can be used to determine the amount of silver iron in the wastewater produced from the electroplating plants. In the precipitation titration, silver iron in the wastewater we add with standard potassium thiocyanate solution. Now you will come across this kind of titration in Form 6. In your Form 4 practical test as well as Form 5 SBA, we will mainly focus on acid-base titration. You may also have the chance to perform the redox titration, in which the reducing agent is react to an oxidizing agent. Now let us look at how to carry out a titration. Usually, a long volume of sample solution is placed in a conical flask with a properly rinsed pipette, and the volume is usually 25.0 cm3. The standard solution is placed in the burette, which is also properly rinsed, and the standard solution has long concentration, and we use the burette to find out the volume of this standard solution, which can completely react with the component with the chemicals in the sample solution. The sample solution have known volume but unknown concentration. The solution in burette has known concentration, for example 0.5 mol per dm3, but it has unknown volume. So we are going to determine this volume in order to find out the concentration of the sample solution. Now, adding a few drops of indicator help to indicate the endpoint of reaction. Do you still remember the common acid-alkali indicators that we have learned before? You need to remember the color of the indicator in acidic medium as well as in alkaline medium. Also, you need to remember the pH at which the indicator change color. I have mentioned earlier that litmus is not a common indicator used in titration because the color change from red to purple then to blue is not sharp enough. Now, in the previous video, we know that sodium hydroxide is not a good primary standard. And if we have a reagent bottle containing sodium hydroxide, we can determine its concentration by standardizing it with a standard acid solution. Did you check what are the common primary standards that can be used in titration? Now, to standardize an acid, we can use sodium carbonate solution, and the sodium carbonate solution can be prepared from a primary standard anhydrous sodium carbonate. So this is one of the primary standards commonly used in titration. To standardize our sodium hydroxide, we need to use a standard acid solution. And you know that concentrated sulfuric acid, concentrated hydrochloric acid, and nitric acid, they are not good primary standard. Now, the common primary standard for preparing a standard acid solution is ethane dioic acid, or its common name is called oxalic acid. The solid has the formula H2C2O4 2H2O, and we can use a known amount of this solid and dissolve it into known amount of distilled water so as to prepare a standard acid solution, which can be used to standardize the sodium hydroxide with unknown concentration. To perform a titration, we have to be very careful to avoid unnecessary dilution, contamination, or any loss of reagents. In a titration, the analyte, that is the sodium hydroxide solution, will be transferred by a pipette to be placed in a conical flask. Now, our pipette must be rinsed properly, first by tap water and then by deionized water, lastly by the solution to be transferred. So it should be carefully rinsed with a small amount of our sodium hydroxide solution. Our titrant, the titrant is the ethane dioic acid solution, and it will be placed in the burette. Now, the burette should also be carefully rinsed by tap water and then by deionized water, and lastly by the solution to be contained, that is rinsed by a small amount of the standard acid solution. Then we need to add the suitable indicator, and we can start our titration. Now, would you please spend some time to take a look at the video. The video shows the technique to be used to carry out the titration, that you have to do it by yourself during the practical test as well as the Form 5 SBA. You can also find these diagrams in your textbook. Now, we use the pipette, of course, together with the pipette filler to transfer our sodium hydroxide solution of unknown concentration. Now, to get the accurate volume, we need to observe the bottom of meniscus and the position of the graduation mark. Then we transfer the sodium hydroxide solution into a conical flask. In the burette, we have the standard acid. We need to add a few drops of indicator to the solution in the conical flask. And we have to read the burette reading very carefully. Otherwise, you cannot get an accurate result. So pay attention at the eye position. Now we start the addition of acid by opening the stopcock. Now pay attention to the right hand and the left hand. Now you have to swirl the solution continuously. At the same time, your left hand is controlling the stopcock, which in turn control the rate of addition of acid from the burette. Now this diagram summarizes the titration process. We have 25 cm cube sodium hydroxide solution of unknown concentration. Add the conical flask. We add the suitable indicator and we fill the burette with 0.1 m ethane dioic acid. And then we take the initial burette reading, for example 10.00 cm cube. Now remember, the burette reading must be of 2 decimal places. We start the addition of ethane dioic acid into the sodium hydroxide and until the indicator change color. This is the end point of our titration. And then we read the final burette reading. The final burette reading, for example, is 30.00 cm cube. Also must be in 2 decimal places. Now from this information, we can work out the concentration of our sodium hydroxide solution. Now the concentration of our sodium hydroxide solution equals to the number of mole divided by volume in dm cube. Now the volume of sodium hydroxide solution used is 25 cm cube, so it should be 25 times 10 to the power minus 3 dm cube. And what is the number of mole of sodium hydroxide? The number of mole of sodium hydroxide equals to 2 times the number of mole of H2C2O4. You can check this from the balanced chemical equation. And how to work out the number of mole of ethane dioic acid? It can be obtained from the concentration of ethane dioic acid, the initial burette reading, and the final burette reading. Adding indicator is one of the methods to determine the endpoint of titration. Errors may arise if we do not choose the correct indicator. Equivalence point is a stage at which the reactants are just completely react. For example, if we have hydrochloric acid placed in the burette and the conical flask contained this amount of sodium carbonate, and we can immediately work out that we need 30 cm cube of hydrochloric acid to complete the reaction. So one way to increase the accuracy of our volumetric analysis is to find a method which can signal the endpoint as close as possible to the equivalence point. You may also need to notice that the equivalence point of an acid-alkali titration may not always be at pH equals to 7. If we have strong acid titrate against a strong alkali, we have the acid in burette and the alkali in conical flask. We can use either methyl orange or phenolphthalein to indicate our endpoint. Methyl orange changes its color from pH 3.1 to 4.4, so you may notice that when methyl orange change color, the solution is in acidic medium. That means an extra amount of acid has been added to the solution. And if we use phenolphthalein to indicate our endpoint, phenolphthalein change color at pH 8.3 to 10. So when phenolphthalein change color, there still have trace amount of sodium hydroxide remains in the conical flask, which has not been reacted with the acid. Now, so either methyl orange or phenolphthalein may impose some error in your titration. But for strong acid and strong alkali, this error is acceptable comparing to the errors arise from poor experimental skills or some other incidents during the titration. If we have a reaction between weak acid and strong alkali, the salt will have pH larger than 7. So for this titration, we need to use phenolphthalein to indicate the endpoint, because phenolphthalein change color at the alkali medium. If we have strong acid, we titrate with weak alkali, the salt solution will have pH smaller than 7. So in these cases, we must use methyl orange. And then lastly, if we have weak acid titrate with a weak alkali, and we cannot predict the pH of the salt solution, so in these titrations, we need to analyze this case by case. Now we will take a look at the choice of indicator in titration. And for the other endpoint detection method, I will talk about this in the next video. Now, this table summarizes the use of different indicators in different titration. Now, just now we talk about strong acid and strong alkali. We can use either phenolphthalein or methyl orange. For phenolphthalein, the color change is from pale pink to colorless. Originally, the conical flask contained alkalis, so the phenolphthalein has a pink color. And when the solution turns to colorless, that means the pH has dropped below 8.3, and this is the endpoint, and we have to stop the addition of acid from the burette. Or we can use methyl orange as the indicator. Now, but please note that the solution becomes orange when the endpoint is reached. Now, please do not say that the solution changes from yellow to red. When the solution turns red, that means the pH of the solution is below 3.1, which is very acidic, which means that extra acid has been added to the solution, which changed the solution to a very low pH, and it is not accurate. The next pair of reactant, we have strong alkali react with weak acid. If strong alkali is present, the equivalent point has the pH higher than 7, then we must use phenolphthalein. Similarly, if we have strong acid, the equivalent point pH is below 7, the salt solution is slightly acidic, then we need to use methyl orange. Now to the last pairs of reactant. A weak acid, ethanoic acid, is titrate against aqueous ammonia, which is a weak alkali. Now, both the acid and alkalis are weak, then we do not have suitable acid-alkali indicator. So we cannot use neither phenolphthalein nor methyl orange. They will not give accurate endpoint. So we can only use pH meter or data logger together with a titration curve in order to locate the endpoint of this kind of titration. This example can be found from your textbook. 0.05 molar sodium hydroxide solution is titrated against this amount of ethanoic acid with the use of a suitable indicator. Now, from this information, we know that the equivalent point is 25.00 cm³ sodium hydroxide solution. The acid-base indicator used in this example should be phenolphthalein. The phenolphthalein in an acidic solution is colorless. When the indicator changes color, this signals that the endpoint is reached. Now, for the accurate analysis, the endpoint should be very close to the equivalent point. To increase the accuracy of the volumetric analysis, we usually repeat the titrations many times. The first titration is called the trial. The results of this trial should not be used in calculation. The trial is just like a rehearsal or a warming up exercise for us to know what would happen during the course of titration. For example, what will be the approximate volume of titrant need to reach the endpoint, and what is the color change at the endpoint. In the titration, B-rate readings are very important, and we need to take the B-rate reading up to 2 decimal places. So after performing the trial titration, then we can move on to the accurate titration. We can do as many accurate titration as we like, but we need to pay attention to the time management and also whether we have sufficient solution to do so many accurate titrations. During the practical test or SBA, we will only accept accurate titration readings if the volume of titrant used is within our acceptable range. The acceptable range is usually 0.2 cm3. That means the maximum volume of titrants or the minimum volume of titrants from your accurate titrations should not exceed 0.2 cm3, and this is a school-based requirement. Now let us look at example 1. In the trial titration, the initial B-rate reading is 0.00 cm3, and when the indicator change color, the final B-rate reading is 28.90 cm3. So the volume of titrant required for the trial titration is equals to the final B-rate reading minus the initial B-rate reading. And then in titration 1, we can work out the volume of titrant for titration 1, titration 2, and so on. And you have to check your results of these titrations, whether they are consistent or not. Now, since the range is 0.2 cm3, and you can see that all our 4 accurate titrations are within the range, then we can work out the average volumes of titrant used. Now, when we are working on the average volume of titrant, we should not include the trial results. So the volume, average volume equals to the results from the accurate titration divided by 4, and we keep the answer to 2 decimal places. Now, so this is the average volume in example 1. Now, similarly, can you work out the average volumes of titer or titrant used in example 2 with the readings shown in this table? Now, there are 5 titrations besides the trial one that has been done in this analysis. Now, don't forget our acceptable range, and then you have to pick those titrations that the results are within the acceptable range. For the titration results that is out of the acceptable range, we have to reject those data. Now we need to reject the trial first, because for every calculation, we do not include the trial readings in the calculation of average. Now if we take 28.00, remember every B-rate readings must be in 2 decimal places, and 27.8 is within the acceptable range. But 28.2, now we can't accept this reading because this 2 has the difference of 0.4. Now then we cannot take titration 3, but we can take titration 4. Now so for these 3 results, they are within the acceptable range, and you can calculates the average volume. Now, but in this titration, you can see that if I take 28.00 as an acceptable value, but I go to the other direction, I discard titration 2 but take titration 3. 1, 3, and 5. These three titrations also give us three results that are within the acceptable range. Now, so in this case, we have two possible average volume. The average volume can be 28.10 cm cube, or the average volume can be 27.990 cm cube. Now, so from these two data, you may be able to work out two different concentrations, and during the practical test, we will check which data is correct. Then we can use the average volume of titer or titrant to calculate the concentration of the reactant in the sample solution. Now, in every volumetric analysis, we need to write a balanced chemical equation where the coefficients are the mole ratio of the reactants. We need to read the question very carefully to see whether the sample has been diluted before the analysis. Don't worry, you only need to read the question very carefully and able to visualize what is going on during the course of analysis. And mole calculation is the most important in the calculation of volumetric analysis. Now let us take a look at this class practice. You have the sample vinegar solution, and 10 cm cube of the vinegar solution is diluted to 250 cm cube. And in this 250 cm cube of diluted vinegar solution, we only take out 25 cm cube of this diluted vinegar to a conical flask, and with the presence of suitable indicator, it is titrate against sodium hydroxide, and 23.50 cm cube 0.05 molar sodium hydroxide solution is required for it to reach the end point. Now, in this question, because ethanoic acid is a monobasic acid, although it is a weak acid, in the presence of sodium hydroxide, ethanoic acid can completely react with sodium hydroxide to form the salt. And from this information, you can work out that the number of mole of sodium hydroxide for complete reaction is this amount. So in this 25 cm cube of diluted vinegar solution, which contain the same number of mole of ethanoic acid, but in the volumetric flask, the number of mole of ethanoic acid should be 1.175 times 10 to the power minus 3 times 10 equals to 1.175 times 10 to the power minus 2 mole of ethanoic acid. Now, it is because from the volumetric flask to the conical flask, we only use 1/10 of the total amount of ethanoic acid. So in the original bulk solution, there should be 1.175 times 10 to the power minus 2 mole ethanoic acid. But this number of mole comes from 10 cm cube of vinegar. So if we want to find out the concentration of ethanoic acid in vinegar, which equals to number of mole divided by volume in dm cube. Now the number of mole is 1.175 times 10 to the power minus 2, and the volume is 10 cm cube. So the concentration of our original vinegar is 1.175 mol per dm cube. Now this is the end of this video, and you should take some time to finish homework 2 and do as many calculation practice as possible. In the coming video, I will talk about using different endpoint detection methods in volumetric analysis, as well as the calculation involved in back titration.